So today we're going to talk about what if it's a 2D motion, projectile, but now angled launch. So when we talk about angled launch really is anything that's not a horizontal launch. So anything that is not horizontal launch. So when we talk about horizontal launch, it was just a ball is like rolling off of a table. But now what's going to happen is we're going to have a ball that's going to be like going up at some angle. I guess technically, let me rephrase that. It could be down at some angle. It's just not horizontal. So anything that's not horizontal is an angled launch. There's two types of angled launch problems that we're going to deal with. There's one called delta y is equal to 0, and then it's not delta y is equal to 0. We'll get to that. But when we start talking about angled launch is probably more common in everyday life than a horizontal launch, right? We don't see a lot of cars driving off of the edge of cliffs, hopefully. We don't see a lot of like people just running off the side of a building and not jumping up and off the side. I don't know why they're doing that, I guess, anyways. So we see it like, or the outfielder is going to try to throw the guy out at home. He doesn't throw a line drive from center field. Okay? Or even a softball pitch isn't flat, right? It's going to have some type of parabolic motion. So it's more common, like you throw a long football pass, all those things. We tend to get an object, a lot of our motions are up at some angle. And if we're just going to be very like generic, we can call that angle theta. Right? So if we're throw something at some angle, I don't care what that angle is, it's going to have a certain velocity. And we could say it's got some velocity of vi. And we can say it's being thrown at some angle with some speed. I throw a fastball as hard as I possibly can at 50 miles per hour at some angle. Okay? That 50 miles per hour would be how fast I throw the ball this way. But when I go through and I make my list of variables, is this my x direction, is this my y direction, or is this some combination of my x and my y direction? It's both, right? So it's all great to say, hey, I throw a 50 mile per hour ball from center field at some angle, how far is it going to go, right? And we could say, well, where is it going to land over here? It's called like a max range kind of problem. But in terms of making our list of variables, it doesn't go in either column, because that's not my VIX and it's not my VFX. So in order to do a calculation with an angle, what we have to do is we have to do a little bit of trig. So the idea is it's called resolving a vector. We can resolve a vector. We can take a vector which has both a speed and a direction, and we can break it into its its x component and its y component. So if we were going to resolve this vector, what we would get is we would get some portion of this right triangle that would be its VIX, right? Its initial velocity in the x direction. And we could get some component called VIY, and this is a right triangle. And if we did some trig functions, because that's theta, I should put theta a little bit closer to my corner. If that was theta, using sine, cosine, tangent functions, we can resolve this vector into its x and y components. I promised you at the beginning of the year that we weren't going to do trig functions, and I'm not breaking my promise, but we can do angled launch. But what has to have happened in order to do an angled launch problem? Someone else had to resolve it for you. So when we do an angle launch problem, I'll word it such like a ball is thrown from center field such that the vertical component of velocity is 10 meters per second. And the horizontal component of velocity, x, is 15. I don't even remember what I said for the first one. So what I would do is I would give you these components, or maybe we'd have to solve for this. I don't ever use that number. We are not going to use VI. Sometimes I might say it, just to kind of put some context there. If I were to take a ball and throw it at 50 miles per hour at 45 degrees, 45 would be my theta, 50 miles per hour, I don't even remember what I said, would be my VI, but then we'd have to break it down into its components, which I would give to you, or given enough information, I'd ask you to solve. Okay? Now, when we talk about, so that's how we get around the trig function. These are broken down for you. But what it is, so opposite over adjacent, opposite over hypotenuse, right, SOHCAHTOA. So opposite over hypotenuse or adjacent over hypotenuse would be a sine or cosine function of theta, but we aren't going to bring it down. So angle launch. Okay, we'll have to resolve a vector into these components. Now, if I go through, and if I take some object, and I were to throw it at some angle, and that angle looks to be about 60 degrees. What this ball's going to do, or this object is going to do, is it's going to do something like that. And maybe parabolic is meant to be symmetrical. Whether I am or not, I don't know. Okay, and it's going to be in the air for some amount of time, and it's going to go some distance. So we could talk about, well, what's my delta y at max height, right? So really that's a max height problem. If I were to say how high does the object go, I'm saying, well, what's the first half? Or I could say how far does it go? It'd be my delta. Now, what if I were to change my angle? What if instead I were to throw this at, say, 45 degrees? Does that ball go further or shorter than if I throw it at 60 degrees? Think about, like, general life experiences. Or if we want to go to extremes, what if I throw something like at 90 degrees, or 89 degrees, almost perfect. The up is going really, really high, and this is going to land like right there, right? So as I go flatter, what happens? It goes further, right? So at 45 degrees, it's going to do something maybe like that. But then what happens when we go less than 45? 45, just so you know, is something that we call max range. It's the theoretical value or angle that we're going to get an object to go at the maximum distance, at the furthest range, maximum range. Now this is assuming the same velocity. So right, if I take a baseball and I throw it at 60 degrees at say 50 miles per hour, it's going to land right here. Still 50 miles per hour, but I throw it at 45 degrees, it's going to go right here. But if I keep changing my angle, so this is my maximum range, if I go then to say 30 degrees, does it go as far as 45 degrees or less than 45 degrees? It goes less than 45 degrees. And at that angle, it's, which one's in the air the longest? 30, 60, or 45? 60 is going to be in the air the longest, right? Which one's going to be in the air the least? 30. Okay, and if we were to follow the path of this 30, it would maybe end up something like that. Now my angles maybe aren't perfect, my parabolas aren't perfect, but my endpoints are intentional. I can't really see that blue one, my apologies on that. Blue. Okay. 30 degrees versus 60 degrees. What do we call those two angles to one another? Math class stuff. Well, if we add them together, they equal. And what do we call two angles that add up to 90? Complementary angles. Okay, so complementary angles, 30 and 60, end up at the same endpoint. 45-degree angle, maximum range is going to go the furthest in the air. So 60, more, 50 miles per hour, right? 50 miles per hour, if I throw it at 60 degrees, we're going to get more VIY than we are VIX. So it's going to go up higher, it's going to make the air longer, but my velocity in the x direction the component isn't as good, so it's not going to go as far. At 30 degrees, I give it more VIX, so it's going to be going faster in that direction, but not as fast up, so it's not in the air as long, so it ends up there. Complementary angles will actually end up at the same point. Why? If you were raiding a medieval castle, and you had a catapult or a trebuchet, or you're trying to throw a pass into your post, or you're trying to throw something over a defender, or a quick pass, the idea is we can, sometimes there's a reason for a 60-degree throw compared to a 30-degree, right? So a 60-degree, I can get it over maybe my castle wall, right? There's my castle wall. That boiling pot of burning oil, I can throw over the castle wall to try to kill everyone inside. So they did medieval times. Or you got your post player, you're trying to throw a lob into the post over the defender. But sometimes we want these short, quick passes because it gives less time to react. So complementary angles are the same. Now I use 30 and 60, but realize this is any two complementary angles. It'd be 10 and 80. It'd be 44 and 46. Okay, 45 degrees is max range though. We get this trade-off of in the air versus total time. So if we take a look at our green 2D motion problem types, we've got two more blanks to fill out. So the last two types are angle launch and if it's a delta y is equal to 0 problem. Okay, so if it's a delta y is equal to 0 problem, it has certain conditions. So this is 2D motion problem types. So we've already gone through and identified if it's horizontal launch, then my DIY is 0. Everything we've done projectile motion-wise thus far has been horizontal launch. But they aren't always horizontal launch. Again, like I said, a lot of things in life are not horizontal launch. Horizontal launch is where the ball just rolls off the table compared to if I were to bounce it off the table and it hits and it goes up at some angle, even though it's still leaving from the table, it gives it more time in the air. So if it's an angled launch, and I know it's an angled launch because the object is thrown at some angle such that it's not horizontal to the ground. It'd be something along the lines of a ball is thrown at 45 degrees. A ball is thrown at 20 degrees. If a ball is thrown at some angle, okay? And I say thrown, remember it doesn't have to be thrown. The car could go off of a ramp, go flying through the air. A person could go running off towards the edge of the building and before they just run straight, or dock. Let's maybe use run off of a dock example compared to off the top of a building. Okay, if you're running down the end of the dock and you're going to jump into the lake, sometimes it's fun just to keep running straight, right? But sometimes we jump up and into the air to get into the lake. But if you jump upwards, that's an angled launch. If it's an angled launch it doesn't really tell us a whole lot. It really tells us something it's not. So what this says, and I see some people trying to read this, and I realize this is kind of, I'll zoom in. This says VIY does not equal 0. Okay? If it's angled launch, that's the part just to the left. If it's an angled launch, then your VIY is not 0. Well, what is the value, you may ask? I don't know, but it's not 0. Maybe you have to solve for it, maybe it's given in the problem. It depends. Do not put 0 in. Maybe that, hopefully that hasn't been a conditioned response. Okay? But with a 2D motion problem, a 2D motion projectile motion is different. A 2D motion projectile horizontal launch is different than a projectile angle launch. Thus far, we've been doing horizontals. So if it's an angle, your VIY does not equal 0, look for it in the problem, maybe we're solving for it. If it's an angled launch, then the next part is the question we got to kind of ask ourselves. And is it a delta y is equal to 0 problem? And if it's a delta y is equal to 0 problem, we would know that because the object starts and ends at the same height. And if it's the starts and ends at the same height, it's the same information that we talked about with a delta y is equal to 0 with max height. Because remember, an angled launch or a parabolic like this, if we had note in the y direction, is really just an up and a down. So if the object starts and ends at the same height, then we can say my VFY is equal to the opposite of my VIY. So in the y direction, my initial and final are opposites of one another. And the time is 2 times larger than the time to max height. Because sometimes we still like to use that max height thing. And if we talk about angle launch, and if we choose max height, we know the velocity at max height is 0. So we could then say, oh, hey, I have a final velocity. Or maybe I have the initial velocity. I'm looking on the way back down. Now, there are some 2D motion projectile angle launch that are not delta y is equal to 0 problem. Here is an example of a delta y not equal to 0 problem. Okay, so if I were to start with my ball here, I can't quite see that. If I start the ball here and I throw it at some angle, it landed here. I started here, it hit here. This is not the same as this. This is not a delta y is equal to 0. But if we were to go from there, that was almost really bad. That almost gets broken glass everywhere. All right, let's try that again. Cut that out of there. If we go from there to there, right, it starts here and it ends here. I'll leave it in. Everyone gets the benefit of watching the teacher screw up every now and then. Oh, what time, Mr. Davies? Hey! Okay, but if it starts there and ends there, they start here, it ends here, that is a delta y is equal to 0 problem. Okay? If I take this ball and I bounce it off the floor, and it didn't hit the ceiling, and it ends on the floor, that's a delta y is equal to 0 problem. Thank you. If I take this ball, and I go like that, that's not a delta y is equal to 0 problem. You see the difference here? Okay, good. Wait, oh. Yeah, I do. Okay, good. That's how that was supposed to be. Okay. Angle launch is just a different type of 2D motion projectile that we haven't dealt with yet. Let's go through a problem, or get started on a problem. I don't know, let's see how it goes. In class, 2D motion in class problems on the back. We'll do number 5. Two-D motion in class problems. Problem number 5. All right. 2D motion, class problems. Number 5 says, an arrow is shot at some angle above the ground such that the velocity in the x direction is 18 meters per second and 23 meters per second in the y. Assume the arrow lands at the same height at which it was fired. Let's make this assumption unless very specifically told otherwise. Okay, so from here on out, unless I very specifically tell you otherwise on an angled launch problem, we're going to assume that it starts and ends at the same height, unless very specifically told otherwise. Couple things: how long is the arrow in the air? How far does the arrow travel? How high did the arrow go? Okay, there's a couple different questions we could deal with. I think quick sketches are helpful. The idea is I have some arrow, and the arrow is going to go like that. Okay, it's going to go with some parabolic motion. There's some information given in the problem that tell us some things from this, but it's at some angle, theta. I don't care what theta is, but it's at some angle, and it's going to land some distance apart. Okay, so we still work through our 2D motion problem types. Is this a 1D or 2D motion problem? The arrow moving through the air. 2D. Black marker, same thing that I've done every other time so far, is black marker is for everything that I know because it is 2D motion. And only because it is 2D motion. Same time. Black marker, 2D motion. Is this a projectile motion problem? Is the arrow moving freely through the air in both the x and y direction simultaneously? Good, good. Okay, so because of that, my ax has a value of 0 meters per second squared. My ay, because that's 0, these are going to be the same. Because it's a projectile motion problem, we know my acceleration in the y direction is negative g, which is equal to negative 9.8 meters per second squared. Is it a horizontal launch or is it an angled launch? Those are your two choices there. Now you got to make a choice. Is it angled or horizontal? An arrow shot at some angle, so it's an angled launch. All that means is I cannot, and you could, I don't think it's super helpful, so I'm going to do this once and I'm going to erase it in like 5 seconds. What that means is this is not equal 0. But I don't think that's worth writing because that's not a number we plug into it. But don't put 0 there. That's all that really tells us. We'll have to pull that from the problem information. So don't put a 0 in for the green marker. So it's an angle launch. Is it a delta y is equal to 0 problem? Does the arrow start and end at the same height?
Yes.
Yeah, I'm out of marker colors. All right, we're going orange, I guess. So because it is, I know that my final velocity in the y direction is going to, because this is 0, this is going to be the opposite of VIY. Okay, it's going to be the opposite. Now, we haven't gone to pull those numbers yet, but we'll get to that in just a moment. So from problem types, that's what we can get. Now, looking at the information in the problem, an arrow shot at some angle would probably is important, such that the velocity in the x direction is 18. I'll switch colors just to help. And it says it's 23 meters per second in the y. So I think I might have used orange for the, red was from the problem, I think. So now I have some numbers such that the velocity in the x direction is 18 meters per second, and it's 23 meters per second in the y. So what is my initial velocity in the y direction? It's 23 meters per second. And in the x direction, this is at 18 meters per second. What this is kind of showing on my little picture, this is going at 18 meters per second this way, but it's going up at 23 meters per second, right? If I was going to resolve my vector, I'd break down into this. Now, tangent function, if we really wanted to, and we probably would like to, but I'm not going to take the time, we could figure out what theta is, right? The inverse tangent function of opposite over adjacent. 23 divided by 28, or I'm sorry, 18 inverse tangent would give us theta, but we don't care. Okay. So that's the information we have. Now, oh, actually, we should fix this then. So because my initial velocity is 23, that means my final velocity in the y direction is going to be negative 23 meters per second. Okay, so that's the information we have now. That's what we're starting. Part A, how long is the arrow in the air? So, how long is asking not how long did it go, but how long, that's a time thing, right? That's how much time has gone by. Now, looking at our list of x versus y numbers, what do you think we've got a better shot at finding time in? Y, right? Because we have 4 out of the 5 variables filled in. So we're solving for time. We have a lot of options, actually. We could choose, we just got to make sure it has time, that's the important thing. So we could use equation 2, because VFY is equal to VIY plus AY times T. I'm going to erase some of these in a second. I'm just going to show you that we have some options. So we could use equation number 2. Equation number 3 says delta y is equal to VIY times T plus 1/2 AY T squared. We could, okay, because it has the T that we're looking for. We could use that. Oops, number 3. I'll talk about number 3 in a second. Number 4 is not a good one because, I'll show you, VFY squared is equal to VIY squared plus 2AY times delta y. There is no T, right? There's no T, so 4 is a loser. I mean, didn't win. Equation number 5 could also work. Delta y is equal to VFY plus VIY divided by 2 times T. I think I had the addition in the right order that's listed. So 2, 3, or 5 are all possibilities. The thing that 3 has going against it is if we're solving for T, there is a T and a T squared. The nice thing is because delta y is equal to 0, we can actually factor out a T, or one of our solutions of T is 0. So the idea is at what time is delta y equal to 0? Well, at time 0, it's at 0, and time whatever. That's the idea. Of these 3 possibilities, I like number 2 because it seems to be the most simplistic in my opinion, but 3 could work and 5 could work. Just do your algebra correctly. If you say, am I doing my algebra correctly? The answer is, I don't know, let me take a look. Final velocity is negative 23. Initial velocity was 23, plus my AY, which is negative 9.8, times our T. Don't do the silly math algebra mistake that I see too often. Say, well, I gotta get T by itself, I just gotta move this over the other side. Negative 23, positive 23, that's a 0. We got to subtract 23 from both sides, which makes us a negative 46 is equal to negative 9.8 times T. And T is going to give us, we're going to get a value of negative 46 divided by negative 9.8. We get a T of 4.69. So that's how long my arrow is going to be in the air. for 4.69 seconds. If you would have chose equation number 3, we have 2 times that my delta y is equal to 0 right here at 0 and right here at 4.69. It's okay, you just gotta factor. There's 2 solutions because you have a t and a t squared. So now that we have our time, we know time here, 4.69 seconds, 4.69 seconds. For part B, the question is now, how far does the arrow go? What's my delta x? How far does that arrow go? What's its range? It's another way to say it. What's the range of this arrow? So, because my acceleration in the x direction is 0, in the x direction, I like to use equation number 3 because it cancels out nicely. A chunk of it does. So equation number 3 looks something like that. But because ax is 0, I get delta x is equal to my initial velocity times t. So delta x is equal to 18 times 4.69. Now remember, it's not really 4.69, it's 4.693877551. And if you're going through some of the homework problems and you say, I'm getting a different answer than you, the first thing that I'm probably gonna, I'm kind of close, is did you use 4.69 or did you use 4.69 blah 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 that your calculator told you that it was, and you should use all the digits and round at the very, very, very end. And we get a final answer of how your arrow will land 84.49 meters away. And if I would have used the rounded value, I would have gotten 84.42. Okay, so it's a difference of 7 centimeters, which you say, well, that's not that big a deal. Okay. Okay, but that's what we should. So this is how we found part A. This is how we found part B. For part C, this particular problem asks, how high did the arrow go? Now, we got to be kind of careful with this, because for how high did the arrow go, that doesn't match the variable list we have. Because the variable list we have is where the arrow starts here and it ends here. Right? This is my initial, this is my final. It was initially going up at 23 meters per second, but what that's going to say is it's going to be coming down at 23 meters per second. It's still going to be going 18 meters per second for my final velocities. That's what that list of variables represents. And if I were to say how high does the object go, what I'm really saying is, what is the max height of that object? So we got to be careful and recognize that this is a different, it doesn't match this anymore. It doesn't really even match this anymore. Because this is from here to here, but now I'm only going halfway. There are a few things we know at max height. We know the velocity at max height is 0. And we know the time from here to here is 2 times bigger than the time to here, because it's a delta y is equal to 0. It's 2 times larger than the time to max height. So the time from here to here is 2 times bigger than the time from here to here, if it's a delta y is equal to 0. Now, the question being asked is, how high? It's really only a delta y part. So we can go through, we have to make a new list of variables. But once again, you have some options. You're trying to figure out how high, what's the max height, that's delta y. The arrow was still initially moving upwards as a VIY of 23 meters per second. It's still a projectile, so the acceleration in the y direction is still negative 9.8 meters per second. But because it's a max height problem, we know the velocity at max height is 0. And we know that the time to get to max height is 4.69 divided by 2. And I apologize, I'm writing pretty low on the board. Makes it hard to see. I'm sorry. I can close my computer if that helps any. I don't know if that's enough to make a difference. Maybe. Once again, we have some options in terms of equations because we know 4 numbers. The key is we must choose one that has a delta y in it. But then from there we can kind of make some choices. So the one we can't use is we can't use equation number 2. Don't use equation number 2 because there's no delta y in it. We could use equation number 3 because we know VI, we know T, we just got to do that algebra quick, divide that by 2. We know 1/2, we know AY, and we know T squared. Equation number 4, we could use final velocity squared is equal to initial velocity squared plus 2 times A times delta y, solve for delta y. We could use equation number 5 as well. So it's kind of up to you at that point of which one we want to use. What do we want to use? 3, 4, or 5? 5? Okay, all right. So someone say 5. So let's take a look at number 5. Delta y is equal to VIY times t plus 1/2 AYT squared. Now, because I'm going to use my time function again, I'm actually going to go back to this and I'm going to get all my decimals back so I can use that again in a little bit. So, my time, when I take that number and I divide it by 2, is 2.346. Okay, so I'll write 2.35, but I'll use my full decimals once again. So delta y is equal to my VI, which is 23, times the 2.35. Again, I'm going to use my full number in my calculator, and I store it, and that's how I can use it more than once. Plus 1/2 times negative 9.8 times my 2.35, again, all my decimals, and then we can square that. And we only square the time. So, interest of time, I'm just going to do some calculator math. I'm not going to show all my steps, is what I'm saying. Assuming I just punch that into my calculator correctly, I get a delta y of 26.99 meters high. So it went up 26.99 meters. Let me just double check that I input that in my calculator correctly. Yeah, that's right. That's what I got. Okay, so sometimes I'll ask you to say how high. I don't know. I try to avoid some of those. It's just a different thing we can do with them. But it's really a new list it's a new list in the Y direction, and you just got to recognize that. So we're going to make the assumption that they start at the same height unless I tell you specifically, and we'll go through an example or two of those. Okay. Still shooting for Monday, next Monday for our test on this 2D motion.